Welcome to my presentation, where I present the design and simulation of a synchronous counter of mod less than 2 power n. And therefore, we are looking at the synchronous counter, where the mod is less than 2 power n. Previously, we designed and simulated a circuit of synchronous counter form, where the order was 2 power n, a counter that was counting from 0 to 7. And I will demonstrate this with the design of a counter that counts odd numbers between 0 and 7. And therefore, we are looking at a counter that is able to count odd numbers. The numbers are between 0 and 7. And I'll demonstrate the design and simulation of this counter using the D flip-flop as the chosen flip-flop for the design. The design process would still take the same form as in our previous design. We will have 3 flip-flops, and therefore our truth table will have the following as the previous state. We'll have the states for the 3 flip-flops as QA, QB, and QC. The next state will also be for QA, QB, and QC. And lastly, we need to design for the inputs to the 3 flip-flops, which are the DA, the DB, and the DC. Then we write the count as follows. So we are counting from 0 to 7, only odd numbers. Initially, we write all the numbers as 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. Then we'll have the zeros and ones interchanging. So that is our count. Next, we need to determine the next state of each of the counts. So 0, 0 being not a valid input, then we represent the next state with don't care terms. 0, 0, 1, a 1, the next count is a 3, which is 0, 1, 1. 0, 1, 0 is a 2, not a valid input, so we represent that with don't care terms. Therefore, being an invalid input, we represent that with don't care terms. A 3, the next state for a 3 is a 5, which is 1, 0, 1. A 4 being even, again, we represent this with don't care terms. From 5, we go to 7, which is 1, 1, 1. 6 is an invalid input, being even, so don't care terms. And lastly, from 7, we go back to 1 as 0, 0, 1. This will mean 0, 0, 1. Next, we use the state transition diagram of a D flip-flop to fill in the values of the inputs. So we can have the transitions as follows: a transition of 0 to 0, a transition of 0 to 1, a transition of 1 to 0, and a transition of 1 to 1, where the inputs are supposed to be 0, 1, 1, 0. So for all the invalid inputs, for all the invalid states, then the inputs will also be represented using don't care terms. And therefore, we can first represent all these using the don't care terms. Then from there, we look at the transition of 0 to 0, will give us a 0. A transition of 0 to 1 gives us a 1. A transition of 1 to 1 gives us a 1. And a transition of 1 to 0 will give us a 0. Next, look at the second columns for QB. QB 0 to 1 is a 1. 1 to 0, a 0. 0 to 1, a 1. and 1 to 0 and 0. Lastly, we have 1 to 1, a 1, 1 to 1, a 1, 1 to 1, a 1, and 1 to 1, a 1. Next, we use suitable K-maps to obtain the reduced form of each of the inputs. Of course, there are 3 inputs. We use 3 input K-maps as follows. For DA, this will be our K-map. So has the 3 inputs as QA, QB, and QC. 0, 0, 0, 1, 1, 0, 1, 1. Then this is 0, 1. We first fit in the values of the don't cares at 0, 0, 0, 0, 1, 0, 1, 0, 0, and 1, 1, 0. So these are the locations of the don't care terms in our given design. Next, we fit in the values of 1. So we have a 1 at 0, 1, 1. So 0, 1, 1 is that location. And a 1 at 1, 0, 1. A 1 at 1, 0, 1. Sorry, this is supposed to be 1, 1, then 1, 0. This is 1, 1, and 1, 0. So that the 1, 0, 1 is this location. Then we can do the groupings. So we can form a group out of these two and a group out of these two, and from which we can write our DA to be equal to our DA to be QA bar QB for these ones, and then or these ones will give us QA QB bar QA QB bar, which is equals to, if you look at this, is the XOR expression, which can be written as QA XOR QB. And that's our DA. For our DB, we use again a 3 input K-map. This is our K-map. Again, this is QA, QB. This is QC. The values are 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. The location of the don't care terms will not change, so we'll have the don't cares at those locations. We fit in the values of the 1, so we have a 1 at 0, 0, 1, and we have a 1 at 1, 0, 1, this one. Then we group. We notice you can group these terms and these ones as follows to form a group of 4. So we group here together with these to form a group of 4s, from which then we can write our DB will be equal to what is common is QB bar. Then finally for DC, we can observe that the K-map will be a K-map filled with don't cares and ones. So if we were to group all of them, then that would mean our DC is a 1. And these are the inputs to the 3 flip-flops that will help us determine or design the count or numbers between 0 and 7. We proceed to simulate these. Okay, so we can simulate these in Proteus. We insert the 3D flip-flops. So 3D flip-flops. So these are our 3 flip-flops. We interconnect their clock signals with a common clock signal being synchronous counters, as previously discussed. Okay. Next, we fit in the values of the flip-flops. So we can use a voltage source. And make sure that its voltage is set to 5 volts. Next, for dB, the input is QB bar. So I tap the inverted output of that flip-flop and feed it as my D input. Then I need an XOR gate. Need an XOR gate, a 2-input XOR gate. Whose inputs are QB and QC. So we connect it to QB and QC, QA and QB, sorry. So this is QA and QB. That's our input. We connect a display section and start with the decoder. That's our decoder. We connect the inputs C to the most significant bit, B to the next, and A to the least significant bit. We can ground the terminal D because it's not being utilized. Then we insert the display, 7-segment display. Here, this is our display section. The common anode. We can do the connections from the decoder to the display. Lastly, we connect this pin to 5 volts, being a common anode 7-segment display. So we connect this to 5 volts. And that's our circuit, which we can proceed to simulate. We can run the circuit. So, and check the count of odd numbers, 1, 3, 5. Okay. So this is counting 1, 3, back to 1. Let's check that the connection we've probably missed out. So this is supposed to be 5. That's okay. Our DC is 5. Our DB is QB. So this is QB. That's okay. Then our DA is QA X or QB. And probably check this connection. Okay, simulate. Yeah, so the connection to the clock was not intact at this point. You can confirm now it's counting 1, 3, 5, 7, back to 1. And that's our counter that counts odd numbers between 0 and 7 using the D flip-flop. Thank you for watching the video.